Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to look at strong and weak acids and strong and weak bases and what that actually means. So we're first going to start with strong and weak acids and go from there. So a common mistake or common misunderstanding that a lot of students have about strength of an acid is that means it has to have a very low pH. So for instance, if something had a pH of 1 or 0 or even a negative value, they think that that is a very strong acid. What pH tells you is the concentration of hydronium ions, which is acid, in a solution. But that doesn't necessarily mean it's strong. What essentially is a strong acid is a molecule that ionizes 100% when it is put into water. So let me explain to you what that looks like. So HBr gas is a polar molecule, and you can bubble it through water, and because it is polar, it will actually dissolve in the water. So the HBr becomes aqueated because it is polar and it's soluble in water, and then it reacts with water to form acid. So what I want to make sure you're really clear on is, even though we call this a strong acid, it's not acid. Hydronium, H3O+, is acid. We call this thing an acid because it makes acid, not because it is acid. So if we follow the rules for Bronsted-Lowry or even the modified Arrhenius theory, we know acids donate protons to water. So this donates its H+. Now, the reason why this thing is a strong acid is it donates hydrogen ions 100% of the time. So when it hits water, it donates its hydrogen 100% of the time, driving the reaction forward to completion. That's what makes it a strong acid. Now, if I have a highly concentrated acid solution, it can have a very low pH, but not donate hydrogens 100%. So a strong acid can have a pH like 5. It just means that I have very little of that acid actually dissolved in water, so it's not producing a lot of hydronium. Anyways, we should finish this reaction. So if this donates an H+, what's left of it? Well, there's Br, but it's lost a positive in the H+, so now it is a negative, so it's Br-. And now what does water become? Well, it's gained an H, so it's H3O, and it's also gained a positive, so it's H3O+, which is aqueous. And this is acid, okay? So again, the strength of an acid is based on how much it ionizes when it goes into water. This ionizes 100%, which makes it a strong acid. Now there's 6 strong acids you need to know. Perchloric acid, HClO4, is a strong acid. Nitric acid, HNO3. And sulfuric acid, H2SO4. So these 3 all have a polyatomic ion in them: perchlorate ion, nitrate ion, and sulfate ion. The other 3 just have a monoatomic anion, which would be HCl, aqueous, hydrochloric acid, HI, hydroiodic acid, and HBr, aqueous, hydrobromic acid. These are your 6 strong acids that you must know, and I do ask that you memorize them. Now, the reason I have a beaker over on the right is for you to understand what this would look like at the atomic level. So if I had a beaker and the beaker was labeled HBr aqueous, there's actually no HBr aqueous in it. Because all the HBr reacts with water to produce bromide ion and hydronium ion, inside of the beaker, that's what we have in a 1-to-1 ratio. So for every H3O plus, I'm going to have a Br minus. And we would call these our major species. The products are called our major species. Now this will help you out a lot when you get on to further in chemistry, because you'll do net acid-base reactions with major species, and you have to make a major species list. So this is something that you would do as you continue on in chemistry a lot more. So again, the major species are what the majority of what is in solution, and we wouldn't include the water. Now, I'm sure there'd be just a few non-reacted HBRs in there, but it's so minute, I wouldn't actually include that in my picture here. So the big thing is, again, when I put a strong acid in water, it ionizes 100%. So for instance, if I had a 1 moles per liter concentration of HCl, it would contain 1 moles per liter of H3O plus ions, because when you balance this stoichiometrically, this is a 1-to-1-to-1-to-1 ratio. And if all of it ionizes and the concentration of, say, HBr here is 1.0 moles per liter, then both products have the concentration of 1.0 moles per liter because it's a 1-to-1 ratio. Strong acids will also conduct very well. The more ions that are there. So something like a 1 molar concentration of HBr would be very good conductor of electricity. So the definition of a weak acid is a acid that ionizes less than 100%. Now, in reality, most weak acids might react, from 5% or below. Some acids react fractions of a percent with water. So again, strong acids react with water 100% to produce hydronium, whereas a weak acid reacts a lot less. So if I use something like hydrocyanic acid as my example, again, it's very polar, so if you bubbled it through water, it would dissolve. Now, it would react with the water some of the time, just some of the time. Okay, so this would still donate an H+, but rarely, I'm going to say. I'm not going to give it a value. You'll learn how to calculate that value when you get to higher levels of chemistry, including chemistry 30. But this is a much less than 100%. Now, because of that, we don't put a single arrow forward. That's showing that the reaction actually goes to completion. This reaction is actually in something we call equilibrium. The reaction does go forward a little bit, but it actually goes reverse even more. Now, if you're wondering what do you mean reverse, let's put in the products and I'll tell you what the reverse is. So the H+ is donated. What's left of HCN is CN. But because CN has lost a positive, it is now negative. And of course, it's lost the hydrogen. So that's aqueous. The H2O liquid has gained H+, so this is H3O+, aqueous. And when I say the reverse reaction, I mean when CN- hits a hydronium, some of the time it actually recreates a water and an HCN. But it's doing this at the same rate that HCN is reacting with water to produce CN- and H3O+. So we call this an equilibrium arrow. And equilibrium arrows are always required for weak acids and weak bases. And this is a topic we look at extensively in acid-base equilibrium further on in chemistry. So that's the big difference. It ionizes less than 100%. So if I was to look at a beaker like this one and it was labeled HCN, I would actually find tons of HCN in there. Lots and lots and lots. Again, because HCN is a polar molecule, it's happy to stay dissolved in water. Now, on occasion, you will find some hydronium and you'll find some CN minus, but the H3O plus and the CN minus are called minor species because you have less of them. The major species for a weak acid ionizing in water is always the reactants. These would be the major species because that's what I have the majority of. Now, stronger acids conduct better and react faster than weak acids of equal concentration for sure. And even if some weak acids have a higher concentration than a strong acid, the strong acid still sometimes reacts faster and actually conducts better. So to be clear, when you write an ionization equation for HCN, you include an equilibrium arrow because the reaction does not go to completion. The definition of a weak acid is not the pH it produces, but rather the fact that it does not ionize 100%. Before I move on, I just want us to look at our acid and base page, which gives us a lot of information. So I'm just going to summarize up a few things. The top 6 acids on this data page represent your strong acids. These are the strong acids. And so you have them available to look up, but it's really important that you start to memorize them. It does help speed things up. So these are our 6 strong acids. And this is acid. Hydronium is acid. Anything that falls below here is going to be a weak acid. So this is where our weak acids begin. And as you go down, they become weaker. So what you'll notice is there's a value here on the right-hand side, and I'm not going to explain it in total detail, but it essentially tells you how forward the reaction goes or how much hydronium is being produced. Now for the strong acids, the Ka values are so big they don't even put them in because it's essentially almost infinitely forward. Whereas when you look at the top of this weak acid section, the first value is less than 1, and so essentially this reacts with water less than 50% forward, and it doesn't produce a ton of acid. Although this would be, on this chart, the strongest of the weakest acids because it has the largest value over here. Now, it gets weaker and weaker acids as you move down the table, so this becomes weaker and weaker and weaker, going down to the very bottom where we end up with water, which is essentially going to be our weakest acid. Now, what I also want to do is show you how you can figure out the ionization equation for a weak or a strong acid using this table. So if I wanted to write the equation for an acid reacting with water, what you could do is you could go to this table, and I'm going to use HClO4 as my example. I could simply write plus H2O liquid and then a single arrow forward. So this would react with water, and that would produce ClO4 minus plus H3O plus. I could do this for every single acid going all the way down this table. So I could do the exact same thing for all of these with a single arrow. But once I get to the weak acids, I would have to put my equilibrium arrow in. So this would be plus H2O liquid equilibrium arrow, sorry about the space, and this would produce H3O plus, but remember it would be a lower concentration of H3O plus than this one up here because it is a weak acid. Strong bases have a very similar definition to strong acids, just slightly different wording. But it says strong bases dissociate completely into ions in water. Of course, this would have to produce hydroxide ion. Now, the difference in word is dissociate. Strong bases don't need to ionize because there already are ions. So ionization is the process of creating ions. Strong bases are ionic compounds that when they are dissolved in water, they dissociate into ions that produce hydroxide. Now here I have a list of what it is. So strong bases can be an alkali metal, group 1 metal, with oxide or hydroxide. Now this is probably, the oxide's a little bit maybe beyond the scope of our course. I am going to explain it on the next page. But it's not going to be my focus right now. The one that you really have to know is the hydroxides. So to make this crystal clear, the examples of strong bases really are things like lithium hydroxide, potassium hydroxide, and sodium hydroxide. These are the ones that you will continuously see throughout chemistry a lot of. You may see a little bit of cesium hydroxide, and then I've added 2 more down here. Most people would say that barium hydroxide as well as strontium hydroxide are strong bases because they do really have high solubility. Based on our solubility table, they're considered low solubility, but I can promise you can dissolve strontium hydroxide quite well. And so these would actually produce 2 hydroxide ions for every 1 formula unit of that substance. But again, I really want to push. These 3 here are the ones you're going to see almost exclusively. So to remind you of what a dissociation equation looks like, I'll use KOH. So you'd have KOH. It would turn into its 2 ions, K plus aqueous plus OH minus aqueous. And again, there's a single arrow forward here because this essentially goes 100% until, of course, you're just not able to dissolve any more in water due to the solubility. So if I was to label, a beaker and it said KOH, aqueous, there really is no KOH together at all unless it's a saturated solution. In that case, there'd be some solid KOH at the bottom. But otherwise else, it's just K plus and OH minus. They're just floating around. Remember that OH minus, that is base. And so these are our major species. I will address the oxide in the next page, but for now, this is what we are going to go with. And it's important that you start to memorize, this definition of what a strong base is, which is to dissociate completely to form hydroxide. And the 3 most common ones are really going to be your lithium hydroxide, potassium hydroxide, and sodium hydroxide. So weak bases have a similar definition to weak acids in that they are going to react with water to produce a small percentage, but this time, of course, it's going to be of hydroxide ion because it's a base, and they're acting as a proton acceptor. So really weak bases fall into 2 major categories. You can have some that are very polar molecules. The only one that we really look at this level is NH3 or ammonia. It's a very common base. I'm going to talk about that one a bit more. And then also anions other than the conjugates to the strong acids. So that would be ClO4 minus, NO3 minus, not HSO4 minus, it's actually an acid, but Br minus, I minus, and Cl minus. You should have these memorized as being neutral ionics. And by the end of the lesson, I'm going to do a review of why they're neutral ionics. The focus now is really going to be on how do I figure out how anions work in terms of being a base, and how does a very polar molecule. So for instance, I'll use an example, something like F minus. That's a base. Now, normally we wouldn't write just F minus. It would be part of some kind of ionic compound. So for instance, I might write something like NaF aqueous, because realistically, the Na plus is an ion in solution, and the F minus is an ion in solution. The Na plus is just a spectator. It doesn't do anything. So when we did spectator ions in net ionic reactions, again, this is a spectator. It's not part of the reaction. It wouldn't be included there. But the F minus is the base because it is a proton acceptor. Remember the idea, a proton, which is a hydrogen ion, is positive. Positive things are attracted to negative things. So that's why it has to be a very polar molecule to be a base, because the negative end on ammonia, which would be at the top of it, this would be the negative end of ammonia, that's really attracted to a hydrogen ion. Hydrogen ions really, really want to attach themselves to that lone pair of electrons. And then once it's attached, it has gained a proton and therefore is acting like a base. So I'm going to write two reactions out, one for NaF and then one for ammonia, just to reinforce how this works. So again, if I said write the reaction of NaF with water to produce hydroxide, I would drop the Na. Most of the time, this metal here is going to be Na or K plus or Li plus, because they're super high solubility group 1 metal ions, and they're inert. They're not going to react with anything. So most of the time when I look at a formula and I'm asking myself, well, is this a base? I check the anion. As long as the anion isn't one of these, and it's with a really soluble metal ion, then I know it's going to be a base. And generally most questions are going to use, group 1 metal ions as its partner because they're very highly soluble. So let's start with the F minus here. So what would happen is F minus would be in water, and the water would donate a proton to the F minus, a small percentage. So it would donate a hydrogen a small percentage, not all of the time. And because of this, this is also in equilibrium. Remember, we always need an equilibrium arrow if we have a weak acid or a weak base, because this reaction does not go to completion. Now, if the F minus has gained a hydrogen, it's now HF, and because it's gained a positive, it's no longer negative, so this is HF aqueous. Now what's left of your water? Well, it's down an H, so now it's just OH, but it's also down a positive, so if it has one less positive and one more negative, then it's going to be negatively charged. So that would be the one for F minus. If I was to do NH3, it looks very similar. I would have NH3 aqueous plus water. Now because the nitrogen is very polar and water is very polar, they're very attracted to one another. And some of the time, again, some of the time, not all of the time, waters will donate an H plus, a small percentage, to the NH3. Because of that, this is in equilibrium and has an equilibrium arrow, and it becomes NH4. Now again, it has an extra H because it's gained an H, but it's also now positive because that is a positive thing. So this is aqueous, and what's left of water is OH minus. So you can see this pattern. We have something plus water Equilibrium arrow, something plus hydroxide. Something plus water creates something plus hydroxide. I really just have to fill in, my starting point and then my end point, and I'll show you a way of doing this using your data book to help you along the way. Now, let's say we had this labeled as NaF. There would be no NaF together because it's highly soluble. You would have Na plus and F minus, and you'd have lots of that kicking around the beaker. But on occasion, you will find an a HF and an OH minus, but in a very low percentage. So here, our reactants are the major species. And this is true for all weaks. So weak acids, the reactants are the major species. Weak bases, the reactants are the major species. For strong acids and strong bases, it's the products that are the major species. Always the products that are the major species. So really what we're looking for at this level for what is a weak base, it has to follow this definition of they react with water to produce a small percentage of OH minus. They're either a very polar molecule or they're anions other than these 5 here, which are neutral ionics. So before I move on to my very last topic of strong and weak, I want to come back to the table here and just explain to you the neutral ionics, but also how to write a ionization equation for a weak base and just kind of show you where strong base is on this page. So to be clear, the neutral ionics are perchlorate, iodide ion, bromide ion, chloride ion, and nitrate ion. The HSO4 is actually a weak acid, and you can see that because it's down here as a weak acid, it's not neutral. Now, let me try to explain to you why these 5 are neutral ionics using the definition of what a base is. What a base is a proton acceptor. So, if I minus happened to come across a hydrogen ion, so hydrogen ion came close to it and was like, oh, you're negative, I really like you, it would turn into HI and immediately ionize and turn back into I minus and H3O plus. It would be like an extreme case of hot potato. It would accept the hydrogen, turn into a strong acid, and immediately give it up. So these things can never really accept a proton because as soon as it would then ionize it immediately, and therefore it's not really a base. So other than those, the weakest base is water. Okay, the strongest base is down here, which is OH minus. This is strong base. What you'll notice is there's no list of 6 or 5 things for you to have for strong bases. You are just required to know them. So remember, these are going to be things like LiOH, KOH, NaOH, CSOH, a group 1 metal cation with hydroxide. It's also nice to know that strontium hydroxide really is a strong base, and barium hydroxide really is a strong base, although I stay clear of using those in any questions at this level of chemistry based on the fact that they are not recognized as being soluble on the solubility table we use basically all the time. What you'll notice when you look at the base side, these are all the conjugate bases. So when you look at the base side of this table, all but one of them is going to have a negative charge because they're going to want to accept protons. So negative, 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 very polar. This is the only one that isn't an anion. Negative, 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 negative. And I could keep going up the table nonstop. all the way to the top, and sure enough, they're all going to be negative values. Now, how do I write an ionization for this? It's basically just the reverse, okay? So these would be our reactants. The bases would be our reactants. So I could put something in like plus water. This would be in equilibrium, but remember again, this side is this is my reactants, okay? And then this would produce this anion plus OH minus aqueous. So I would write this out this direction, not that direction, because this is the base reacting with water. I'm just showing this for you to have a good understanding of how it's done. So for instance, let's say I was told I had potassium cyanide and I needed to write an ionization equation for potassium cyanide. I could simply go, okay, it needs to react with water. I'm going to react water in here. What's it going to become? Well, it's going to gain a hydrogen from water, so it's going to become HCN. So that would be on the product side. I'd have my equilibrium arrow, and then plus OH minus. Again, I'm writing it in this direction if I was asking for a base ionization. And essentially these two things are just interchangeable, right? So for the next question, it could be this becoming this, or this becoming this, or this becoming this. And I would always put OH with it, and I would always put water with it. That's kind of a trick way of figuring out how to write an ionization equation for a weak base. And again, as a review, if I wanted to do it for an acid, I would just write water on this side. And of course, acids are making hydronium, not hydroxide, and I would write it in the forward direction. So over here, this would be the strongest base. This is your first weak base. And they actually become weaker as you move up the table. So this would be weaker, 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 getting up to water, which is the weakest base. And then of course we have ionics. So this thing here, this HOOCCOO minus, is essentially like the weakest of the weak bases on this table other than water. The next two things we're going to look at are two-step acids and bases. At this level, it's not critical to know this at a deep level, but it's a nice to know thing. And I get a lot of questions about them, so it's nice to address them at this point. So the first one I'm going to look at is a two-step acids, which essentially usually come from a non-metal oxide and water, or water plus oxygen. And if you're wondering, what are you talking about these non-metal oxides? I'm talking about things like nitrogen monoxide or nitrogen dioxide or carbon dioxide, sulfur dioxide gas. Okay, these are all gases. And when they mix with water, either in the atmosphere or when they're bubbled through water, when you make pop or soda, they have an acidic effect. The most common one that you'll probably see is carbonic acid forming carbon dioxide. Now, if you have a soda stream or whatever, you can see this process essentially happen. So what ends up happening is carbon dioxide gas is forced under pressure into the water, under pressure. Higher pressure above the liquid with the gas is going to increase the solubility of the gas in water. So for instance, carbon dioxide and water would react, and then what would essentially happen is you keep your two hydrogens, then you have your carbon, and you have three oxygens, so it makes HCO3 aqueous. Well, that's carbonic acid. The carbonic acid then itself has to react with water in another step, in which it would donate its hydrogen ion. Now this is a weak acid, so it's not going to be 100% of the time. Now if H2CO3 lost one hydrogen, it would be HCO3. And of course, it's lost one positive value, so this is negative, and then plus H3O+. That's why carbonic acid, or I should say carbon dioxide dissolved in water is considered an acid because it goes through this step and it eventually produces hydronium. One that you would see a lot in the media, especially when it comes to environmental chemistry, is sulfur dioxide, which is produced in coal burning is a really bad one. Coal burning power plants produce lots of sulfur dioxide. It goes up into the atmosphere. It reacts with some oxygen and with some water, and it actually produces sulfuric acid. And without proper scrubbers in coal generated power plants, you can have really high acid rain content around a power plant. The next one we're going to look at is a two-step base forming from oxides. So earlier in the lesson I talked about strong bases being a group 1 metal ion with an oxide, and I would address this at a later time. I'm going to address this right now. So if I had potassium oxide, which would be this, I need to have 2 potassiums for every 1 oxygen, and I put that in water, it would react with the water to produce 2 KOHs. Now if you're wondering, what? 2 KOHs? I just think of it this way. I have 2 Ks, I have 2 Os, I have 2 Hs, 2 of each would produce 2 KOHs. The 2 KOHs would then dissociate into ions, which would be 2K plus aqueous plus 2 OH minus aqueous. So our second step is the dissociation, which produces strong base. So things like Na2O or K2O or Li2O really are strong bases. It just takes 2 steps to be produced. Again, the things on this page are nice to know, and a lot of students have questions about them, so I have addressed it at this time, but they are not a huge curricular point or thing that we need to know at a deeper level at this point in our chemistry career. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.